Hi everyone, thank you so much for joining us today. Today we have Jehanzeb with us. He's a computer vision PhD student at TU Graz in Austria. His research is focused on self-supervised and unsupervised representation learning techniques for deep neural network robust to distribution shift on test time. Today he will be talking about his research on adaptation to distribution shifts in an unsupervised manner. So thank you so much for joining us today. Over to you, Jandeep.
Hi. Thank you so much for the invitation, Amit, and thank you so much for the introduction as well. I just quickly jump into my slides. Okay, so you should see my screen. I hope, right?
Yeah, we can see it.
Yeah. Okay. Perfect. Yeah. Thanks. Um, Okay, so I would, yeah. So as I've already been introduced, my name is Mohammed Jehanzeb Mirza, and I'm a third-year computer vision PhD student at Technical University of Graz in Austria, supervised by Professor Horst Bischof. And the research focus of my PhD is mainly on unsupervised domain adaptation to distribution shifts. Yeah, we'll just directly go to over the agenda first of all. And first of all, I would be discussing test time training methodologies, which I've been working on recently for different kinds of input modalities. For example, images, videos, and point clouds. Um, we would go into test time training, and I would tell you everything what exactly is test time training. Then the second part of the talk would be on vision language foundation models, where I would be discussing two recent works of ours, which in which we use the text-only supervision or this unpaired data to kind of adapt these vision language models to the downstream data sets. Yeah, so first of all, the first part of the talk is going to be predominantly on test time training. So yeah, it's kind of a new or a niche field. So let's just go over it in a little bit of detail. Yeah, so this was a paper which was put forward by Yu Sun from UC Berkeley in ICML 2020, which was titled as actually test time training, and that is how the name was coined. But it has a lot of similarities to online domain adaptation, for example. So I can just quickly go over the paper, and then you can probably understand where I would be heading towards. Yeah. So in the paper which I'm talking about, first of all, what they do is that they have these that they have this joint training phase, which would basically be that you have your main feature extractor or the backbone, which we call is this represented by theta e here, and then you have your two task heads. One is the main classification head represented by theta m, and one is your self-supervised head, which is represented here by theta s. Yeah, so the task is pretty simple, which is basically this joint training phase in which you want your theta e to kind of learn these discriminative representations to classify what are different categories, for example, cat, dog, or a giraffe, for example. And then there is this self-supervised loss or self-supervised training objective as well, which is just trying to predict the rotation of the images. So we can just randomly rotate the images, and then the task is just to kind of predict what is the rotation of the original image. And why is it called self-supervised? Because of course, we can just rotate it in any manner as we want, and we kind of have a control or the true labels, which are just the rotations of the image. Yeah, normally what we'll do is that we'll just train a network, and then when we have when we have test data coming in, then we would just freeze our network weights and then test it, right? But this paper actually proposes a kind of a different solution, which they name as actually test time training, which is kind of an intermediate phase in which they assume that distribution shifts are kind of naturally occurring as a system is being deployed, and now they want to adapt to this auto distribution test data. And how do they do it is very simple as well. So they just so during their test time training phase, as they do not have any labels from their auto distribution test data, then they simply solve this rotation prediction task, which is their self-supervised task here represented. Yeah, so since you can generate the labels of this auto distribution test data in a self-supervised or an unsupervised manner, then you can just have an adaptation signal, and then you can just adapt the representations of this theta e and kind of try to model the distribution of this out of distribution sample. Now the third part is of course pretty simple. Now you do not need to use the theta s or the self-supervised task head, but you actually want to classify what is your image. Is it a cat or a dog, right? So this is done by using only theta m. Now here, one thing which you would have noticed is this unsupervised adaptation objective is pretty important, and this is something which we kind of try to design in our couple of works which I would be presenting. Yeah, so because and this unsupervised adaptation objective is simply important because we do not have any labels for our test data, right? So we need to kind of have this unsupervised adaptation signal somehow. Yeah, so first of all, I would be talking about test time training for image data, where I would be presenting a couple of recent approaches. So the motivation is pretty straightforward again. If we have everybody in the machine learning or the computer vision community already understands that if we have a network which is tested on the test data which is coming from a similar distribution to its training data, then the network would ideally perform pretty nicely or stably. But whenever we have an auto distribution test sample coming in, then the same network would start to misbehave in certain ways. Here, for example, it could probably predict some erroneous output like a cat. Now the goal of this test time training is to kind of correct these predictions on the fly as the network is being deployed, so that it can actually give us the correct output. Yeah, so again, this line of works comes from this paper from ICML. You should check it out. Pretty nice paper. Okay, so these are the distribution shifts on which one of the focus of the evaluations in our paper lies. This is from ImageNet C from Hendricks and Dietrich et al. Yeah, so these are 12 or I think 15 distribution shifts which we kind of tackle in our work, which could be Gaussian noise, short noise, which could probably be naturally occurring if we have a faulty device, or there could be plenty of other reasons as well. Okay, so what we kind of noticed is that one reason for network not performing optimally could be the activation distribution mismatch, or the intermediate responses which are being generated by the network. So there could be kind of this mismatch between the activations which are generated by the network whenever we have an in distribution sample or we have an auto distribution sample. So here, for example, we have a clean training data which would kind of hopefully give us something like a normal distribution just for the purpose of visualization. But let's say now we have this OOD, or this auto distribution test data coming in, then the activation distribution could be a little bit skewed, which is kind of represented here by red, or at least I try to represent it. Yeah, and the goal of this test time training would simply be to map this red activation distribution to the green. So this is something on which 3 of our works are based on, which I will be presenting next. Yeah, so the first work which I would be going into is based on batch normalization, and this is one of the most peculiar layers I feel inside a deep neural network. And the purpose, although it seems pretty simple, is a little bit, yeah, in some manners, a little bit strange. So the basic goal is just to normalize your activation. So you just calculate the means and variances of your incoming batch, and then you basically just normalize your activation responses, right? But the behavior of this batch normalization layer is not the same during training and testing. And what do I mean by that is that during training, what it does is that it calculates the running estimates of means and variances inside the network, and just calculates it over the entire training data. But during test, it just freezes those means and variances, and just uses them to normalize your testing data. So you could probably easily guess what the problem could be. The caveat I feel could be that if you have the testing data which is coming or which is coming from a different distribution and is not really related to your training distribution, then you could have this mismatch of means and variances, right? So this is something which we try to correct in our first work, which would basically just be adapting the means and variances estimates as each outer distribution testing sample is being encountered. So here we can so this was this first paper which I presented at CVPR 2022, named as "The Norm Must Go On: Dynamic Adaptation to Distribution Shifts in an Unsupervised Manner," which we just refer to as DUA in this talk. And here we have this visualization of the activation distribution, where we have this the distributions coming from our source model. So red would represent the corrupted distribution, or the distributions generated from our corrupted data, and the yellow would represent the clean training distribution, right? Yeah, so we can see that there is kind of a mismatch between these distributions, and this is one of the reasons which we found was actually the problem, why the network was actually misbehaving when outer distribution sample is encountered. As I said, so DUA would simply just, as the name suggests, the norm must go on. The norm, or the normalization, would actually be going on during our test phase as well. And by simply aligning the means and variance estimates, we can actually align the activation distributions inside the network, and that is seen here on the right. And this actually helps the network to adapt to this outer distribution sample. Now, I mean, we do it by simply aligning the means and variances. So we could also do it in a brute force manner. And by brute force, I simply mean that we can simply have some distance metric of these activation distributions, and then we can just minimize some kind of a distance metric, and we can just try to map them together, right? And this is something which we presented recently at this year's CVPR 2023 in Vancouver, where the problem setup is basically, I should say, the solution is pretty straightforward. As you can see here, we assume that we are given a deep neural network which is trained on this clean training data, which could be ImageNet dataset, for example. And now what we do is that we have this offline collection of training data statistics, and that would simply be that we have our training set. We just forward propagate through a frozen network. We have our activation responses, which we calculate after the normalization layers inside the neural network. And then I mean, we just make the most basic assumption that they hopefully follow a normal distribution and can be parameterized by means and variances. So we have these means and variances estimates, which we keep as a memory bank throughout our network, and calculated over the entire training set. So after after this offline calculation of offline collection of training statistics, we just have this as a memory bank and not really our training set anymore. And now, as at test time during deployment, whenever we have this batch of data coming in, batch of auto distribution data coming in, we again calculate the same means and variances of the activation responses at the exact same point inside the network, and then the next task is pretty simple. We can just have some distance metric. In this particular paper, we found that simply an L1 loss was actually working pretty nicely for our particular case. Yeah, so after calculating this loss, we can just backpropagate to the network and adapt the parameters of our original network and just test on this auto distribution samples. Yeah, so it turns out that it works out pretty nicely. But many or some critics here might question that, oh, okay, so this activation distribution mismatch or this alignment is kind of well studied previously, but there is one slight twist here, which is that first of all we do it right inside the network or right throughout the network, and not only at the penultimate layer or the output of the feature extractor, but right throughout the network. This kind of gives us this dense feature alignment. And secondly, we kind of have this whole volume which we want to kind of align, and not only so in simple PyTorch terms, not only the channel dimension, but also we want to kind of align these per pixel values inside these channels. So this kind of helps us in some particular task, which I would later go into in detail when I'm kind of explaining the results. Yeah, so here first we go over the image classification results. So these are from a ResNet 18 backbone, and source here would represent the error which is generated by using a frozen ResNet 18 trained on ImageNet dataset, or the clean ImageNet dataset, let's say. And these are other baselines. Here you can see that ACMAD is kind of a little bit worse than CFA, one of the other recent papers for image classification, but it has huge gains on object detection. Here we have some online learning curves, which I would like to go into a little bit detail. So here on the x-axis we would have the time in seconds, and the y-axis would just represent the mean average precision. And the task is to kind of adapt a network which is object detection network which is trained on the original Kitty dataset, and then adapt it to different weather conditions. For example, Kitty fog, Kitty rain, and Kitty snow. And here we can see that that the other baselines perform pretty badly, but our ACMAD is first of all more stable, and then also achieves the best results, let's say, very quickly. Yeah, judging from the curves. Then we have some other interesting scenarios where we just let an object detection system just run in the wild, and there are changing weather conditions. Here on the left we have this specific adaptation to a specific weather condition, but on the right the weather conditions are kind of coming interchangeably. So we start with the network which is trained on clear Kitty, on Kitty clear, and then we just adapt to fog and snow and then rain, and then we go back to clear, and we again see and we also see here that ACMAD is actually also kind of able to adapt very nicely to the clear weather as well, and not really hurting the performance on the original pre-trained network. Yeah, then there are plenty of other scenarios in which we or continuous online learning scenarios in which we test our ACMAD. On here is one scenario in which we kind of go from clear to clear, and then to fog, and then to snow, and then to rain, and then to clear back again. You could check out the paper. But an important thing which I would actually like to go back here is that that why is it helping for object detection is simply because of this dense alignment strategy here. For image classification, it probably does not matter too much, because there you just have to come up with one particular label. But when you are thinking about object detection, then the detector would kind of need to have this holistic image, or this holistic understanding of the entire image, in order to kind of generate first of all the localization of boxes, and also the classification corresponding to those particular boxes. Yeah, so here just quickly showing some qualitative results where we test our ActMad. So the bottom would be ActMad adaptation in foggy weather condition. The middle would be without adaptation, and then the top would be, of course, the base YOLO model. And here we see that ActMad also performs pretty nicely. I will just go over it a little bit, and then we can just move on quickly. Yeah, there is some. I mean, you could basically see that ActMad is trying to, or is able to detect objects in very heavy fog, which are also kind of not really clear with the clear eye, with the naked eye. Here you can again see some good sequences. Yeah. Yeah, the video is on the ActMad website, so you could easily look it up later. Okay, so we can go forward for test time training for video data now. And in the video paper, we kind of want to tackle these kind of distribution shifts. All these kind of distribution shifts, like Gaussian, defocus, short noise, or contrast, which could actually also naturally occur in the video data as well. Yeah, so these are I think again 15 kind of distribution shifts, if I'm not mistaken. Anyway, so going forward, quickly jumping to the video test time adaptation paper for action recognition, which we also presented this year at CVPR by my the project was led by my co-author Wei Lin, and I was also a joint first author on the paper. Yeah, so basically what we again do is we use this ActMad feature alignment feature alignment methodology, where we have this activation distributions calculated from the clean training videos, and then we have this at test time, whenever we have this corrupted test video coming in, we do this feature alignment just like ActMad, right? But here we can also take or take the advantage of this temporal nature of videos, or this temporal dimension in videos as well, where we could simply generate two augmented views of this corrupted test video. We can pass them to the network. We can have this feature alignment on both of these generated views, and then later on. We also have this consistency of predictions between the outputs, because we would assume that however augmented our videos are, we would hope that our network would give us the same predictions for both of these augmented views. Yeah, it works also pretty nicely. This is also at the time it was the first paper to solve or to study this task of test time adaptation for videos. Yeah, so here we test our methodology Vita on 3 different benchmarks: UCF, something version 2, and the large scale Kinetics 400, and we see that our method also performed pretty nicely on these 3 data sets. Then we also have again a scenario where there are interchangeable distribution shifts, like clear to Gaussian to clear to Gaussian again, and our beta represented here by green is outperforming other baselines here as well. Okay, so quickly moving towards test time training for point clouds, and this was presented at ICCV this year, and this is also the first method which we put forward for point clouds, and this is This is these are the distribution shifts which we encounter or can encounter in point clouds. For example, there could be distortion, or there could be some kind of background noise which could be induced due to plenty of reasons, maybe due to the capturing LiDAR scanners, or there could be other corruptions like cutout, which could be because of occlusions, etc. Yeah. So so here I would just quickly give you an overview of our paper, which we name as MATE. Masked autoencoders are online 3D test time learners, and the name actually gives up what we are trying to kind of achieve. So yeah. What we would basically do is that when we have this test a test input, which is an auto distribution test input, we would just simply mask it. We would pass it through the encoder. We have our linear representations. Then we pass it through the decoder. Have our reconstruction, and we can simply solve this distance metric between the reconstruction and the original auto distribution sample, and we can just simply kind of adapt our encoder weights, and then we can just simply classify with the adapted encoder for our online evaluations. Here, I would just quickly go over the detailed methodology of MATE. So first of all, of course, I mean, we make use of this recent line of work, which is this masked autoencoding, which basically just masks aggressively the point cloud or the image data, and then the task is just to reconstruct. Yeah, and we borrow it from the recent ECCV 2022 paper for self-supervised learning, point MAE. You should also check that out. Pretty nice paper. Yeah, so just going over the methodology. First of all, as I initially explained with the original test time training phase, where they use this rotation prediction task for the joint training, we replace it and find that for a 3D point cloud classification task and to adapt to this auto distribution point clouds at test time, masked autoencoding is actually a more suitable task. And what do we basically do is that we have this with clean training data with us, and we would basically just want to train in a joint manner our encoder to kind of learn these discriminative representations to classify the samples to correct class categories, and also to help the decoder for the reconstruction task. Here we have an input sample. We first would simply with random masking throw away 90% of the input points. We pass it to the encoder. We get our later representations, and then we have our classification head represented here by theta c, and we have our decoder head, which is represented here by theta d. The task of the decoder is simply to reconstruct the point cloud, and yeah, and we learn it by using the L2 chamfer distance between the reconstructed points and the ground truth points, and the classification task is simply learned by using the cross entropy loss. Yeah, so we train this network jointly, and then at test time, since we do not have any labels from our auto distribution test sample, we can simply now use this use the reconstruction loss, or this L2 chamfer distance between our reconstructed points and the original points, and just minimize this loss and adapt our encoder weights, and then use this adapted encoder to classify our auto distribution sample in the end. And yeah, that is kind of the basic overview of what we do. There are plenty of other evaluations in the paper, but here I would just quickly, due to time constraints, I would just quickly go over one data set, which is ModelNet 40C. And yeah, this also, so model and 40C benchmark also proposes 15 different kinds of corruptions, similar to ImageNet-C, but in the, of course, in the 3D domain or the point cloud domain. And here you could see the source classification accuracy, and the joint training would just be a frozen backbone, but learned jointly for the main classification task and the task of reconstruction. TTT is the original TTT paper, which uses this rotation prediction as the auxiliary self-supervised objective to kind of adapt to auto distribution samples, and Meta Online is our adaptation. So you could see that we get pretty healthy gains when we average over the entire 15 corruptions. Okay, so this was this brings me to the end of the first session, and now I would be quickly talking. Yes, I have some time. I would be quickly talking about the recent work, or the recent line of work which I've been doing, and that is concerned with adaptation of vision language models using text only supervision. And what do I want to achieve here is that I have a vision language model, for example, CLIP. I would like to adapt it to these downstream data sets. Could be any data set, for example, ImageNet even. By mostly using text only supervision. I will get into this in detail in a couple of minutes. Okay, so the motivation behind this line of work is pretty simple. So we all know these recent advancements in multi-modal VLMs, or vision language models. They typically have, for example, CLIP. They typically have this vision encoder and this text encoder. The vision encoder would, of course, encode the images, and the text encoder would give you features for your text. Yeah, but what we but how do I visualize it is that due to their large scale pre-training of these vision language models, I would go into that in a second. These vision language models are actually projecting the embeddings at a common embedding space, also termed in papers as the CLIP embedding space, right? And by using this or having this combined or shared embedding space gives us the opportunity, or this unique opportunity, I should say, to kind of train a network on one of the encoders to classify one kind of data, and then you can just use this cross-modality transfer property of the CLIP embedding space, or due to the CLIP embedding space, and put this network on the other encoder as well. What do I basically mean here is pretty simple. What do I want to achieve is that, for example, I want to train a network to classify text. Here it is just simply represented as this text classifier. And yeah, the goal is to simply classify the descriptions, which, for example, here is shown as a flamingo has pink feathers and a long neck, right? This is the description of flamingo, which we get from an LLM. I would go into the details in a second. And yeah, so we basically just input these textual descriptions of these instances into our text encoder, get our text embeddings, and the task of this classifier is simply to classify these embeddings to the correct class name, right? And then what I found is was pretty interesting at the time, at least, that you could actually simply just plug this text classifier or this network on top of the vision encoder to classify the visual data as well. And that stems from the property of this cross-modal transfer. And this is a paper which we would be presenting at NeurIPS later this year, which we term as laughter. Yeah, so one of the main highlights, or let's say one of the works which we did or spent most of the time, was to come up with this text data set. And this text data set should ideally replace visual instances, right? So the goal would be to kind of replace the visual instances, for example, the photo of a flamingo with the description, or how does a flamingo look like, right? So what do we do is that we just simply query a large language model, for example GPT-3 here, to describe what does a category looks like, right? And here the category could be flamingo, cat, dog, or any category from your downstream data sets, right? Yeah, so we have this bunch of prompts. For example, describe an image from the internet of a category. And yeah, so since we know the category, and we'll be getting the responses from the LLM, we can easily match these descriptions to the correct categories. And of course, now we are moving towards a supervised learning objective. So to learn this text classifier in the end, right? And then we what we found helpful was that there are some handcrafted prompts which are provided by the original clip paper. And if we mix these descriptions which are generated from the LLM by and with the handcrafted templates from the clip paper, we could come up with this text data set which could be used to train this classifier, right? And here is an overview of the methodology in our particular scenario. First, what we'll do is that we'll have the class names from our downstream data sets. In this case, let's assume we have cat, dog, and bird, and we would just prompt the LLM to give us these descriptions of these different categories, and then we would of course also have these handcrafted templates. As I said, we just mix them together to come up with this text data set. Now we have this text data set here on the right, and the goal now would be to, as I said, to classify the textual descriptions of the visual instances to the correct class names, right? We input the descriptions, get our embeddings here, and now we just simply have this text classifier, and we could actually train it with a simple supervised loss function. In our case, cross entropy loss. So we have our descriptions. We can just have these, because we also have the class names associated to these particular descriptions. We find that that since the text dataset is pretty sparse, so we need to kind of regularize it by adding or sampling some Gaussian noise, and this was particularly helpful. And yeah, so during the training, we can just simply update the classifier weights here, and yeah. Moving towards the second part of the methodology, since I said that this text classifier was also able to classify visual data, so in the second stage, we use this text classifier to give us pseudo labels, and how do we basically do it is as follows. So let's assume we have this image of a dog, a pug. In this case, we generate two views of this dog. One would be heavily augmented, shown at the bottom. One would be unaugmented view. Yeah, and this is this particular setup is kind of borrowed from fixed match paper from NeurIPS 2019, if I remember correctly. So the upper branch would actually simply just give us the pseudo labels, and the lower branch can give us the class logits from the augmented version. So there are a couple of things which need to be mentioned. Why do I actually call them as pseudo labels? It's simply because since we have an unaugmented view here, so we would actually assume that our network would produce more would produce more certain outputs for this view. But since the view is heavily augmented here, our network would probably not be so certain about this about the predictions from this view. So simply we can just put it to cross entropy loss again, because I like it so much, and then we simply update these randomly initialized weight vectors, which is taken from ECCV 2022 paper, visual prompt tuning. We update our classifier weights. We update the layer norm affine parameters inside the vision encoder, and we update the prompts, as I said. So by iterating over the training set of our downstream data set, we can basically also adapt this vision encoder. But yeah. So moving towards the results, we tested it extensively on 12 different benchmarks, and we saw improvements on all of them, or mostly. Here I show laughter star, and laughter star just represents results without the pre-training text classifier. And laughter would be our complete pipeline, and these are kind of just for an eye candy. You can also see the improvements by using the text only pre-trained classifier here, and the improvements are pretty consistent over the 12 benchmarks which we have seen. So these are so here coming towards some ablation results, where we have some results of the text only pre-trained classifier on visual data. And here we see that the GPT plus templates would gives us the best performance of this classifier. So that is the reason why we use it. But there are some particular problems. First of all, we can simply see here that there are some fine-grained data sets like flowers or this describable textures data set, where laughter is not really outperforming the other unsupervised fine-tuning baselines. And there is also some problem if you look closely with the results which we get by using different kinds of dataset generation strategies. For example, even simple templates was giving us 58.1% accuracy, and by using the GPT description plus template was giving us only a minor improvement, and the improvement even gets lesser by using the dataset specific templates, which is only 0.5. So this was kind of hinting towards that maybe the GPT descriptions were not so helpful. And this actually is a pretty nice finding, which led us to our next paper, which is under review right now. But I can just quickly go over it as well, which basically just says, which is well known in the community as well, that better text dataset would give us better classification results. I mean, there is no false statement in that. Everybody should agree, right? But this is the laughter prompting strategy. Laughter is this paper which I just presented before, and here there were a couple of problems why the text only pre-trained classifier was not really working so good. So one of the problems which I kind of realized was that after looking at the descriptions which were generated by the LLM, was as follows. So let's assume we can just take a couple of examples. One from the describable textures dataset, and the describable texture dataset is a fine-grained dataset used for describing textures, or the task is actually to just name what kind of texture it is, right? And there are plenty of different textures like banded, yeah. So when I was prompting the LLM to give me a to describe what a banded looks like, so it was actually describing the snake banded, and because banded is also somehow a snake, but not really the texture, right? And then it even became funnier for me when I looked at the descriptions of fritillary, which is a flower, mind you, but it is also a butterfly, which I also learned later when I was looking into the descriptions. And instead of describing fritillary as a flower, it was describing fritillary as a butterfly, right? So in our next work, what we basically do is that we have this targeted prompting strategy. And by targeted prompting, I mean, what do I mean is that, for example, we have this data set as which is textures, and the task would be to kind of just name what kind of texture it is, right? So we could simply just prompt the LLM with this additional superclass context, which would be, for example, in the case of textures, we can just say describe what a banded texture looks like. And when we did that, so it actually started to give us descriptions which were more targeted, right? And if you remember correctly, I said that that the goal is to kind of replace the visual instances by textual descriptions. So looking at the description generated on the left, we see that that goal is not really fulfilled, because it doesn't really describe what kind of a texture it is, but it's describing some kind of a snake or a butterfly here, right? And in case of fritillary, I just added an additional superclass context, which is flower, because I know that there would only be flower categories inside the flowers 102 data set, and it actually started to give me descriptions of the fritillary flower. So yeah, now rest is actually borrowed from the laughter paper, or the first stage of laughter paper. But the main contribution is to kind of present this targeted prompting strategy here. And here I would here I'm kind of showing the targeted prompts which I use for the ImageNet rendition dataset, which contains these renditions of the original ImageNet categories. For example, cartoon rendition or DeviantArt rendition or sketch rendition. We just prompt the LLM by providing it with this additional context about the kind of rendition which is kind of expected in our downstream dataset. We prompt the LLM GPT 3.5 DaVinci 003, I think, and we have our targeted descriptions generated here. We can just simply train a classifier using the old ways, which I kind of described in detail earlier. Here is again a detailed description of what exactly do we do. We have these targeted class descriptions, and then now what do we want to do is that that we just want to train this classifier, which was also done in the first stage of laughter paper by using a supervised cross entropy loss, and then we would just use this classifier to classify the visual embeddings coming from the images of the downstream data set itself, right? Yeah, so pretty straightforward, I guess. But this small change in this prompting strategy, or this targeted prompting, actually helps us quite a bit. So here we can just look at a couple of examples like this. So I showed this dataset specific template strategy, which we also use for generating the datasets and training this classifier in the laughter paper, and the performance improvement did not seem too much. But here, if we average it over, I think 8 datasets we tested in this paper, it was more than 3.1% already, just by using this targeted prompting strategy. And if you again remember, or just to take you back a little bit, in the second stage of laughter, we were generating these pseudo labels by using the text classifier. And if we have a better text classifier, the pseudo labels are better. Pseudo labels are better. Life is easy. We can easily fine tune, or we can better fine tune the vision encoder by using a good supervision or a better supervision. And here we represent a comparison with the full laughter pipeline, which is represented here as tap star, and we see that we actually already outperform our laughter paper as well, which is currently under review. Yeah. So just to reiterate, the top table is only this text classifier results, and the bottom is actually using the post stage of laughter, also the second stage of unsupervised fine tuning by using unlabeled visual data. Yeah, and this also brings me to the conclusion of my talk. I think I presented a lot of stuff. Yeah, so first we went over test time training methodologies for image data. Then we went over test time training methodologies for videos. Then later we presented an approach for point clouds. Then at the end, moving towards the vision language models, I presented a couple of approaches which do fine tuning of the VLMs by using images and languages, and then by using a better text dataset generation strategy, which is referred to as TAP, or targeted prompting. Yeah, and that should be it from my side. But of course, I should always thank all my collaborators who actually made all this work possible, and they're actually pretty much scattered all around the world, which is pretty nice. Okay, so that's it from my side, and I should also thank you for joining the talk today. And if there are open questions, please feel free to yeah put them up. I'm here.
Yeah, we have a few questions.
Yes,
Salman, you can go.
Thank you so much. Thanks for a wonderful presentation. Can you go back to the slide number 28?
I can go back to the slide number 28. Wait a minute. Yes.
Okay, couple of questions here. First is why the Gaussian noise helps here? Because of the scarcity of the data set, or is there any other insight that we are missing?
Actually, I mean, this is actually an interesting question, and I'm actually looking into it more in detail. But in the paper, we found that this text classifier was actually just overfitting very easily, right? So the since language is way more sparse than images. So this was one of the reasons. And in the future, if we have a better way of expanding this text data set, I feel that Gaussian noise might not be needed, but this is currently what I can actually answer. So this is actually to avoid overfitting and is acting as a regularizer.
Okay, so do you think the type of text classifier used may change the effect of the Gaussian noise? So, for example, if you are using a type of text classifier which cannot get overfitted easily, that may change the overall behavior.
Yes and no. It's because in our work we are actually just simply using a one linear layer. So it's nothing. So it's not too deep in any case, right? We already mentioned it in the limitations of the paper that we were not able to actually train a deeper network. So for this particular scenario, I feel we were not able to make it work. But as I said, that the main bottleneck lies here in the text data set.
And one more question. You also train while the B part when you use
Yes,
pseudo
exactly.
labels to
Yes.
train. So you also update the text classifier weights as well?
No. Sorry. Here. Yes. We
Yes.
do. Yes, we do. Yes.
So what if do you try any experiments in which you freeze the text classifier weights and just uh, update the vision encoder? Because I'm thinking since the later paper you presented in which you basically
Yeah.
said that the quality of the data set was not good. So in that case, if you don't update the text classifier weights here using pseudo labels, can it improve the performance of that your laughter paper? Sorry, I mispronounced the
Yeah.
name.
Laughter. Yes. So so
Yes.
so this is so this is the laughter paper, right? So
Mhm.
I must have some evaluation somewhere, but
Mhm.
I'm probably mixing some evaluations. But I must have done it, but I don't really have a concrete answer at the moment. But I think there should be some evaluation in the paper.
So at the end, like the main thing is that using pseudo labels does improve the performance if you update the text classifier weights.
Yeah, it
I
does.
was
It
just
does. It
thinking.
does. It does.
Okay.
It does. It does. It does. Yes.
Okay. Okay. Thanks.
Yeah. Yeah. Sure. You're welcome.
I had another question. So
Yes.
recently, I was listening to a talk on self-supervised learning, and in the pretext task, what mainly in self-supervised learning they do is that they perform some kind of let's say augmentation or some kind of maybe rotation, which you mentioned in the first slide, and they predict the rotation, and then they fine tune it on the downstream task. So what I was thinking is that maybe if we add the distribution shifted data set in the pre-training task or the pre-test task, and maybe use it as kind of a contrastive learning. So the distributed shifted data set is kind of a pair for of the actual data set. So maybe do you think that can improve the downstream tasks?
Are you referring to this or the previous papers?
Uh, n- I'm not talking about this multimodal. I'm talking about
Okay.
the
Okay.
yeah.
So yeah. So I mean, you could actually replace your self-supervised task with any task. There is a paper, TTT plus plus, in Europe last year, which actually uses a contrastive learning objective. But I feel this is a little bit of a unfair thing, in my opinion, simply because when we because what they do is basically that they have this two views, or this augmented view and this unaugmented view, and then they kind of have this contrastive objective. But I personally feel that is a little bit unfair, simply because it violates the motivation of test time training, and the motivation is basically that you cannot really predict the kind of distributions which you would be encountering later on. So in that particular scenario, the test time training methodology or this motivation was designed in order to kind of adapt to distribution shifts on the fly. But definitely, I mean, this has actually already been shown. So I mean, this can
Yeah,
definitely be done.
I'm thinking more like so it can maybe do zero shot adaptation shift without test and training.
Zero shot adaptation. I mean, that would be. I mean, if you don't know the if you yeah. I mean, zero shot would be a little bit difficult, I feel. Um, yeah.
Yeah, and from this, I want to ask that when you use like the example of fog and uh, clear data set,
Yep.
I think it was KTD or I don't know what data set.
Yep.
How many examples do you need to make a distribution shift? I wanted to ask. Yeah. So, so
Um,
f-
uh,
yeah,
I mean,
going from fog to snow, how many examples
uh,
would you need?
how many examples would I need to adapt? You mean?
Yeah.
Okay. So yeah, I mean, it was actually saturating pretty quickly. But I have the time in seconds, and not really the adaptation. But so in total it was 3,700 samples in the Kitty data set. So I mean, my maths is failing me a little bit, so I don't know. It should be not more than 500 or something. When after this point, particularly after 15 seconds, the improvement was actually not too much later on.
Thank you.
You're welcome.
If you don't have any more questions, we can end this session.
Yeah, I think there are no more questions from the audience. So
Yeah. Thank you very much. It was a
yeah,
lovely talk.
yeah, you're welcome. Thank you so much.
Take care, everyone. Bye.
Bye.